Right, so let's talk a little bit here about moving on to this new topic now called the real number system. This real number system here, topic itself incorporates as well and includes binary operations, right? Now, I just want to run through some aspects of the real number system. Most of it you'll actually know. You all probably don't know it, not casting aspersions. You all probably don't know it in a formal sense, but a lot of the rules and concepts you all would have met them already, right? Now, the real number system is basically the set of real numbers. So this is the real number system itself is a set of real numbers, right? Of course, the set of real numbers, of course, is denoted with that double struct capital R. I'll talk a little more about that in a couple of minutes. This is the set of real numbers together with the binary operations, and I want to introduce that concept of a binary operation immediately. Together with the binary operations, multiplication, and then of course the other one is and addition. Right? So those three things together, they constitute what is called the real number system. Now, in terms of what we call the real numbers, you all probably met this already, but there are different number sets, right? So for example, the most basic number set is the number set that you use to do your counting with. So the counting numbers are called the correct name is actually the natural numbers. Right now, for all these number sets, in terms of the symbol, the specialized symbol for them, they consist of what is called double struct letters, right? So natural numbers uses a capital N. Well, a typical set would use a capital letter in any case, but it uses a capital N, right? And to make it special, it is what you called, and this goes back to the typewriter days, right? So you basically have an N, and then you write or type a letter N right next to it like that there. So that's what you call the double struct N. Of course, that takes a bit long in terms of writing it itself. So the typical way to write it now is just to do that slanted part of the N double itself. So this is the set of natural numbers as a symbol for it there, the double struct N, right? Now in typeface, it might look a little bit better. Right, that's a symbol there, like how you will see it in your exam paper and so on and so on, right? Let me just increase the text size a little bit so it'll look a little sharper. Right, still not big enough. Let's say this here, right? So your double struct N, right? Set of natural numbers. So those are the counting numbers. So the set of natural numbers is an ordered set starting at 1, 2, 3, 4, 5, and so on and so on. Right? Now, there are some operations that you simply cannot perform with the natural numbers, but we'll get into those details a little bit after. Then you have now the integers. Now, the symbol for the integer is actually the double struct Z, like that there, not I, right? So the set of integers, there is no first term of it. It is an ordered set. There is no first term. It is also an infinite set as well. So it has these so-called negative whole numbers like that, 0, and then the natural numbers there included in the set of integers as well, right? So the natural numbers is a subset of the set of integers, right? That is your subset symbol, right? Good. So you have the integers, right? Now, there is a number set, how to say that, includes the integers, and these are what you call the rational numbers. So the rational numbers are basically the set of fractions, right? Now, of course, whole numbers, positive, negative, whatever, all of them could be expressed as fractions in any case, right? So the set of rational numbers, which is the set of fractions, and the symbol is the double struct Q, right? That one is especially difficult to type. So let me to write, sorry. So let me show how it would look in typeface itself. Right, so that's how it will look in typeface itself, right? The set of rational numbers, right? Of course, I wouldn't use R for rational because R is already real, right? Now the set of integers is a subset of the set of rational numbers there. And of course, this is a subset of that as well, right? So the natural numbers is a subset of the set of integers. The integers is a subset of the set of rational numbers, right? Now you notice there isn't an actual formal set called the whole numbers, right? Whole numbers is just a concept, is a layman concept that helps people to distinguish between, well, integers and decimals and fractions, right? So they say whole numbers because it is not a fraction kind of thing, right? But there isn't actually a set in formal mathematics known as the whole numbers, right? Right. So rational numbers. Now, there are numbers that you cannot write as fractions, right? So, and you all would have met them as well. Some of them, that is, irrational numbers, right? Irrational numbers, for example, pi is an irrational number. E, Euler's number, right? Which is roughly 2.7, whatever it is. And of course, we met a lot of irrational numbers when we were doing add math, right? For example, these so-called radicals, root 2, root 3, etc., etc., etc. Those numbers simply cannot be written as fractions, right? So therefore, those are numbers that cannot be written as fractions. But I mean, they do have a value. They do have a location on the number line, let's say. Now, when you take the rational numbers and the irrational numbers and you join them together, you form what is called a set of real numbers. So the real numbers now itself is the joining together of the irrational. Now irrational basically means not rational. The symbol for the irrational numbers, well, you use a set complement symbol there. So you say Q prime. So there isn't really a, how to say, separate symbol for the irrationals, right? So the real numbers now is formed, as I was going to say, by the set of rational together with, what you don't put plus, you actually put union together with the irrational, right? So the real numbers is basically like an all-encompassing number set, right? So now all of these sets are infinite, but the irrational, of course, this list, I mean, there are infinitely many irrational numbers, of course. Now, you can't list the real numbers, right? Like how we were listing the natural numbers and integers and so. And it is even more difficult to actually write down a definition of the real numbers. So what you visualize the real numbers are is basically the number line, right? So all of the points on the number line now is that basically constitute the set of real numbers, right? Now, anyway, as I was saying, right now we are accustomed with working with the real numbers. The real numbers could be used to represent any measurable quantity or anything like that you come across, right? Now, eventually we'll learn, well, not eventually, I mean, when we go to Unit 2, we'll learn that there is a number set that is, how to say, of a different order, or there are some numbers that actually, some quantities that cannot be described or located on the number line itself, right? But we'll meet that at some other point in time, right? Sorry, I was just fixing up the page display there. Right. So anyway, so that's what the real numbers is. But the real number system is the real numbers together with multiplication and addition, right? Now the axioms of the real number system is what I want to go through first. Right. Now, an axiom is basically a mathematical statement that is absolutely true, cannot be proven as being false. It actually sometimes is an axiom is, you could say, is a statement that is so profoundly obvious and simple that you do not need to be able to prove it true to accept it as being true, right? So an axiom is something that is always true. It is basically like an assumption upon which you would base a theory. That's what you call an axiom, right? So the axioms of the real number system sounds very fancy and all that, but I guarantee that most of this you all would have met it already, right? Now I have the list actually typed out in my notes here, so I'm actually going to copy and paste this here. Sometimes when I copy and paste into I'm leaving out some of them actually. Yeah, sometimes when I copy and paste into from Microsoft Word into Microsoft OneNote, some things go missing, right? So I still want to just run through this here, right? So let's wait for it to be pasted. Taking its time. Beautiful, right? Right. So I have it kind of grouped together there under the different types of axioms there. Now, most of this, I am pretty sure that you all will know most of this already, right? So the first group of it, let me try to, does this have the option of spacing things out? Probably doesn't, Probably doesn't. But this is not really a word processing thing. Okay, well, I tried to change the settings, but it didn't space out. But anyway, so we have there's actually 12 axioms, but the 12th one I'm actually not going to bother with it, right? Because it is just it's just strange. It wouldn't contribute to our discussion anyway. So I've grouped them together into the different types of axioms. So you have what is called the operation axioms, and I'm sure you all have heard about the associative law before. The associative law is when you have to perform a binary operation. Well, I didn't even say it was a binary operation. A binary operation is basically a computation, a calculation, or basically any combination of two elements from a set that is computed and mapped onto another element. So for example, an example of a the binary operation multiplication, if I say 3 times 4 is equal to 12, that's how a binary operation works. It takes two numbers, performs something, performs some computation that is defined in some way or the other, and it results in a single number itself. So a binary operation takes two elements of a set and maps it onto a single element itself, right? So 3 times 4 is equal to 12. It's called binary because you have to have two things combining. If I write 3 multiplied by, and I don't say what is multiplied by 1, I'm not making any sense. If I say 2 plus, and I don't say what I'm adding it to, I'm not making sense, right? So multiplication and addition, you have to have two numbers with it. That's why it's called binary. Okay. Now binary operations actually is supposed to be, well, it is on the CSEC maths syllabus. But sometimes years go by and they don't bring any binary operation questions. Anyway, binary operations itself, we'll come to that, right? Anyway, as I was saying, so associative law, I'm sure you all know the associative law. So with the associative law is when you are trying to combine three elements or three numbers together. X, Y, and Z here are just generalizing numbers from the set of real numbers, right? So if I want to say, let's say for example, I want to say 1 plus 2 plus 5. Naturally, because it's addition, you only do 2 at a time. So you could say 1 plus 2, and then the answer for that you add it to 5, right? But if you change the order, not the order so much, but if you change which pair you are doing first, actually get the same answer. It doesn't really matter, right? So associative law has to do with how you pair off numbers in order to add more than 2 or multiply more than 2 together, right? So the associative law, I'm sure you all would have heard about that before. Commutative has to do with the order in which it is written. So for example, 2 plus 5 is the same thing as 5 plus 2. That's what? That's a commutative law. So the commutative law is of addition basically says that what? Addition is commutative. I mean, that's kind of obvious, right? 2 plus 5, 5 plus 2 is the same thing, right? But that's actually a law or an axiom of mathematics. It is so basic and profound. How would you even prove that? How would you prove that 2 plus 5 is 7? Right? You know, there's a way, but we are here to discuss that. So the commutative law of multiplication says that what? Multiplication is commutative. Now, there is no commutative law for subtraction, because subtraction is not commutative. As if I say 5 take away 2, I get 3. 2 take away 5 is not 3. 2 take away 5 is negative 3. So there is no commutative law of subtraction. There's no commutative law of division. Division isn't commutative. 10 divided by 2 is 5. But 5 divided by 10, what did I say? Sorry. 10 divided by 5 is 2. But 5 divided by 10, that's not 2. That's a half. So you get a different answer if you switch it around. I'm sure you all would have heard about that. Distributive law, but you all have been using that your entire life in your algebraic life, I should say. Because I'm sure you all would have dealt with when you're doing algebra. If I give you 3 multiplied by x plus y, right? Or 3 multiplied by x, and we put a number there, 3 multiplied by x plus 6. I would say what? 3 times x, obviously, I would do that, plus 3 times 6. Why do you have to do that? Because of the distributive law. The distributive law says that multiplication distributes over addition. Multiplication distributes over addition. So you have to say 3 times x and you have to say 3 times 6 as well, right? So this will be 3x plus 18. Listen, I'll meet that already, right? Most of the things here, you'll meet it already. Maybe it wasn't, formally defined like we are trying to define it here, but you'll know it. Let's move on to the identity and inverse axioms. If I bold this, it might make it a little bit more readable, right? Identity and inverse axioms. So, first of all, the additive identity. The additive identity exists. There's an element called 0. Let me put in the actual word there, called 0. The symbol obviously is, well, I mean, all I know what a 0 look like. Such that, and something went missing there, right? X plus 0 is equal to, quite a bit of it went missing. 0 plus x, and whether you do x plus 0 or 0 plus x, I didn't have to repeat that because if x plus 0 and 0 plus x is the same thing because of the commutative law, right? But anyway, either way you do it, you will get what? You just get back x. God, not that. You just get back x, right? Listen, of course we know about that already, right? 0 is what you call the additive identity. Because anything added to 0, you just get back the same number you started with, right? Now, with the identity, then there exists something called the additive inverse, right? Now, when you talk about an inverse, right, an inverse is actually a concept that is lost on a lot of people, right? Because if, you approach anybody in the street and you tell them, hey, what's the inverse of 5? Right? Most people will say 1/5, right? But actually, when you want to talk about an inverse is a concept that is specific to an operation. So for you to ask somebody what is the inverse of a number, you have to tell them under whatever operation itself, right? So I'm going to skip out number 5 temporarily, and I'm going to jump to number 6. So we spoke about the additive identity. Let's talk about the multiplicative identity. There is something called the multiplicative identity, right? Where you call it actually unity, and of course the symbol of unity. I mean, another way to say unity is to say 1. Okay, so there's an element called unity such that x multiplied by 1 so x times 1. Oh, so much of this didn't copy and paste properly. Anyway, x times 1 is equal to 1 times x, which is just x. We know that already. You take the number 1, you multiply it by any number, you get back the same number, right? We know that already. So the multiplicative identity is 1. So again, when you talk about an identity, you have to talk about the identity with respect to an operation. The only time y'all would have encountered the concept of an identity is probably when y'all were doing matrices, 2 by 2 matrices. You know, they talk about the identity matrix 1 0 0 1, because if you take anything and multiply any 2 by 2 matrix and multiply it by the matrix 1 0 0 1, you get back the same matrix you started with. Okay. Anyway, moving on to inverse. The inverse is a concept that is specific to an operation. You could only talk about an inverse after you have spoken about an identity for a particular operation. So an identity is an operation specific element. So for example, as I mentioned already, the fourth axiom we have there is that the additive identity is 0. The multiplicative identity is 1. You add 0 to any number, the number doesn't change. You multiply any number by 1 or multiply 1 by any number, you get back that same number, right? You could only talk about an inverse after you have spoken or mentioned or obtained what is called the identity, right? So anyway, the additive inverse. The inverse of an element under addition is the number that you are going to add to that element in order to get the additive identity, right? So let me say that again. An identity is always defined, my apologies, the inverse of an element is always defined in terms of the identity for a particular operation. So if I ask you, what is the inverse of, let's say, I use this as an example just now, the inverse of the real number 5, I have to state the operation, right, under addition, right, under addition. So what I need to investigate here is, okay, well, first of all, what is the identity for addition? The identity is 0. So the inverse of 5, right, is what I'm going to add to 5 in order to get 0. So 5 plus what will give me 0? And obviously there the answer is what? The answer is -5. So the inverse of 5 under addition is what? -5, right? That's what that's what inverse is about. Inverse is always spoken about with respect to an identity, and an identity is something that depends on the operation you are talking about. Let's talk now, again, I'm still talking about identity, but I want to talk about, let's say, the identity with respect to another operation now instead, right? Right? So if I ask you another question, or similar to what I asked you there, what is the inverse of 5 under multiplication now? So the question is now is what the identity on what's the identity under multiplication? The identity, first of all, under multiplication is 1, is unity, right? So the question is what is 5 multiplied by what is going to give me unity? And obviously the answer there is what? 1/5. Oops, write that a little bit neater. 1/5. So the inverse of 5 on a multiplication is what? 1/5. Right? Now going back to what I said before, that typically people think about the inverse as being, if I give anybody a number and I tell them what's the inverse, they will more than likely tell me the reciprocal, right? So 1/5 is the reciprocal of 5, and it is the inverse of 5 on a multiplication. So inverse and reciprocal is not the same thing. Reciprocal is a very specific concept related to fractions in arithmetic, right? But inverse itself now is a more fundamental concept in mathematics. Inverse has to do with, first of all, an identity, which has to do, and even before all of that, with what operation you are talking about. Right? So I'm sure you all knew about the operations involving 1 and 0 with respect to multiplication and addition respectively. But again, we are trying to kind of formalize our understanding of the real number system here. Right? So there, that is where we are talking there about additive identity. And once you have an additive identity, you could talk about an additive inverse. Then there's a multiplicative identity. And going along with the identity, if the identity exists, you could talk about a multiplicative inverse. So an inverse is a per element value. You get the inverse. You don't talk about the inverse element. You talk about the inverse of an element. The inverse of an element depends on the operation you are talking about. And for each operation, there is an identity, right? So inverse is a per element concept with respect to a specific operation, right? Now, the last part of it, which is the order axioms, are more or less used in solving linear inequalities. Now, there are some concepts with respect to solving a linear inequalities that you all, I'm sure, are very, very familiar with. So let's say, for example, I give you something like this. X minus 1 is less than 5. I think most people will then go on to say that x has to be less than 6, right? But the operation that actually took place there is what? What took place there was x minus 1. What you did is you added 1 to both sides. 5 plus 1. So x minus 1 plus 1 is just x. X is less than 6. And this is what you call your solution set. And so on, right? Good. Now, the fact that you could add a number to the both sides or subtract as well, it works to subtraction as well. So if I, for example, have x plus 1 is less than 5, I could then go and subtract 1 from the both sides. But subtraction is kind of like addition of a negative number, right? So it works to subtraction as well, right? So what you would say is that x plus 1 plus negative 1 is less than 5 plus negative 1. So x itself will be less than 4, right? In other words, you could subtract a number from both sides. You don't have to do anything with the inequality sign, right? Now, the fact that you could add or subtract the same real number from the both sides, that is what you call the invariance of the order operation under translation, right? Or you could say translation invariance of order. Now, once you say statements such as greater than, less than, etc., right, that represents order. To say 3 is less than 7 means that in the ordered set, 3 comes before 7, right? So inequalities are also what you call order relationships, right? So under the axiom of translation invariance, you are able to solve a simple linear inequality like this, like these, what I have on the right hand side here. You could just add or subtract, but subtraction is really addition of the negative. You could add or subtract the same number from the both sides of an inequality, and the inequality will still hold. It will still be whatever it is less than, right? There's another one as well, transitivity of the order of order. Let's say, for example, that there. Well, I mean, it is kind of verbatim what I'm going to put here. Transitivity, you don't really use transitivity so much in solving linear inequalities, although there are cases we will meet. Will we meet that in unit 1? Probably not in unit 1, where there are some things we will do in unit 2 where we might have to utilize this transitivity here, right? So if x is less than y and y is less than z, then x is less than z. Listen, that is so blatantly obvious. Again, there's no way to prove it. That's why it is called an axiom. It is true, but it is so fundamental you can't actually prove it, right? Or for sure you cannot disprove it. So if x is less than y and y is less than z, then x has to be less than z. That's what you call transitivity, right? I'm moving on. Trichotomy, exactly one of the following is true. I suppose I have some words here before this thing. So let me go back over here and delete that. So this is not number 11, right? So given a given any two real numbers, exactly one of the following must be true, right? That is, given any two real numbers x and y, exactly one of the following things has to be true. As either x is less than y, or y is less than x, or x is equal to y, right? So if I give you any two real numbers, is either the two real numbers is going to be the same, or let's say I give you one in your left hand, one in your right hand. Let's see. Is either the two, what is in your left and what is in your right, is going to be the same thing, or the one in your left is going to be less than the one on your right, or the one on your right is going to be less than the one on your left. Listen, obviously, right? Any pair of real numbers, you will always find any of those things occurring, right? I really can't think of any other thing that actually could be true. I give you two real numbers, is either they are equal, one is less than the other, the first is less than the second, or the second is less than the first, right? There's nothing more to say concerning that. The last one, scaling of the order operation, is something. Oh, when I typed in there, some things got shifted down a little bit. I could fix that by doing this. Yeah. Scaling of the order operation, right? Now, we use scaling before I actually go into the law itself. We actually use scaling in solving linear inequalities as well. So if I take, for example, 2x being less than, let's say, 8. 2x is less than 8. I mean, everybody knows how to solve this here. If I take the number a half and I multiply it by the 2x, I could take the number a half and multiply it on that side as well, right? Once the number you take to multiply on the both sides is positive, you do not need to switch your inequality sign. That is basically what this law is saying there, right? So a half by 2x, a half of 2x is just 1x, so x is less than 4. We know how to do that. Now, of course, you would say divide by 2, but dividing by 2 and multiplying by a half is the same thing, right? Anyway, the law or the axiom that enables you to just divide by a number throughout, or multiply by a number throughout, a positive number, that is this last order axiom here, which is the scaling and order. So if x is less than y and z is a positive number, then you can multiply z on both sides, and the inequality remains true, right? So this is not a copy and paste error here. This is just an error in what I actually typed there. So if x is less than y and z is positive, then x by z is also less than y by z, right? So basically that tells you, again, if you have an inequality and you multiply the both sides of the inequality by a positive constant, a positive real number, you do not have to switch around your inequality sign, right? So I just wanted to run through these axioms of the real number system before we get into binary operations itself, right? Now, binary operations, we mentioned two binary operations already. That is, multiplication and addition. But in our next session, we are going to look at general binary operations, pretty similar to what you all would have seen in those, well, it is on the CSEC math syllabus itself, right? So that's more or less it I have to say concerning this topic here. These are just things you kind of, you kind of just learn them off, although most of it you already know. But it is stuff that is they don't really ask you for it, to tell you the truth. It's just that it's just some facts about this real number system that you have to be very familiar with itself, right? And formally familiar with it in this case, yeah, right? So anyway, that's it for this video here. So whenever we meet again, it will be to discuss general binary operations.